So it says like this object experiencing like 300 newtons from the right, right? Experiencing 300 newtons here, and 200 newtons from the left. So obviously, it's going to move from the right, but what's the force that it feels? How do I figure that out?
So yeah, well, it's just going to be the vector sum of those. Now, because they're right and left, if we go right by 200 and add that tip to tail with left by 300, then we end up with an excess, a net force of 100 to the left.
That's it?
That's it. Yeah.
Okay.
Yeah. So that one you don't have to do with free body. It's just because they're all horizontal. You don't really have to write free body diagrams. Right. They just mostly, if they totally cancel, there'd be zero net force. Okay, but they mostly cancel, so there's a little bit of leftover net force. Okay.
No, I don't like those, but
So if it's going from 100 to the right and 100 to the left, and it crushes the object, it feels zero net force.
No, it might still get crushed. That's fine. But it depends how you define the system. If you're defining the system as, think of it this way, like let's say you and I are both pushing on an object. If the system includes all of us, then the forces acting on the object are irrelevant, right? Because you see what I'm saying? The net force acting on the object is zero. Now, if you look at, let's say this.
So it's like the force relative from the starting point?
Yeah, I mean, it doesn't really, just because a net force is zero doesn't mean that there are no internal forces going on. It just means that in the system of the object itself is not going to be accelerated because the external forces acting on the object add to zero.
Right.
Now, internally, there's a bunch of stuff going on. Like internally, there's going to be some elastic deformation of the object, and then the materials. So there are going to be some internal forces going on that are going to cause it to do this.
Yeah.
Okay, that makes sense. Okay. Mm-hmm. Well, I'm gonna go through something right now. All right. Yeah, I think you want to see this too. It's tension stuff, and it's kind of.
I have 2 questions left, and I want to.
Well, there'll probably be time. I think there'll be time at the end. Okay, click them close. Click them close.
All day today.
Click them close. What's that?
You and your hunger, would you like a candy?
Sure. I'll take a candy. What do we got?
15 minutes practice.
ATP boosters.
ATP boosters, right? Adenosine triphosphate. Call me biology with it.
You making fun of silent?
What?
You making fun of silent?
Absolutely.
I support that.
Sure. Sure. Wait, what about the half?
Get along. Mm-hmm.
Half more long.
What's that? There you go.
Would you like some
Your wishes might come in.
glass cleaner?
Actually,
I wouldn't use that. It's probably chock full of.
you have hot chocolate every day.
Hmm?
You have hot chocolate every day.
No, I haven't had it in ages actually. This is a backup in case I forget my coffee creamer in the morning at home. I got my backup hot chocolate just in case. I'm not a black coffee drinker. Okay. Okay, let's move up. We got a couple things to do here, and then I'll give you guys a work day tomorrow. How's that sound? Okay, so we want to talk tension today. So I need to record this. Push go. Oh, I am recording. Okay, so we want to talk tension. Tension is just defined as force directed along a line. A line, a flexible line, meaning a line could be a rope, could be a cable, could be something like that. So it's not a difficult concept, but like if you're going to grab a rope which is attached to a weight, well, from the perspective of the weight, what's actually providing the lifting force here? The rope is, right? And so the rope, so the force is going to be directed up along the rope. Now, whenever you deal with tension, you know that the flexible line is always going to follow the lines of force because it's flexible. So you got to close those up, guys. You got to get this stuff. So if this is our, let's say we have a cable on a suspension bridge. So here's one of the vertical supports, and there's another vertical support, and here's the cable right there that's maybe supporting a road underneath, right? So here's the road, and to make things simple, let's just assume there's only one cable here attached to the road. There's actually going to be a whole bunch, right? Well, we'll put a whole bunch. We've all seen bridges that look like that. So if I go to this point, let's just focus in on one point. Like, how about the point right there? In what direction is the tension acting? And if I just took a piece of that cable right there, the piece of the cable is being pulled by the rest of the cable. In what directions would it be pulled?
Down.
Or no?
The side.
Yeah, it's being pulled in that direction and in that direction. Because the cable is defining the directions of the net forces that are acting on it, right? So if we took that piece of cable, so there's that piece of cable right there, right? I just cut out of the cable. We're just going to look at the force vectors acting on that one little loop of cable. There's going to be one pulling in that direction and one pulling in that direction. The net force has got to be zero, doesn't it? Because it's stationary. It's not accelerating. You get what I'm saying? But the lines of force follow that flexible line. Because what would have happened? It's a cable, right? So it's flexible. It can move. What would happen if one of the lines of force was like that way?
The bridge.
What would happen? Bridge would collapse. Well, the cable would move, wouldn't it? Right? You see what I'm saying? Because the cable follows the lines of force. Right? You get what I'm saying? I mean, it can move freely. Like if I had a piece of rope up here and I'm gonna pull something, well, the rope is going to align to the directions of force, however you want to think about it, or the lines of force are aligned to the rope. Because if they weren't, they would adjust themselves, right? It's flexible. So you can literally like see the lines of force acting on a line, meaning a cable or a rope or something, if there's some tension in it, because they're going to follow the direction of the rope, okay? So then, lines are useful to us, right? We can, we pull stuff with lines, but we can't push stuff with lines. You can't push a rope. Does that make sense? Like if I'm dragging something across the ground, walking in this direction, I can't get it to go that way with the rope, right? I can only pull it. I can't push it. So maybe I don't know. Maybe it's better to have a handle instead of a rope then that's attached to it, so I can push it both ways. What's the advantage of a rope? Can you think of advantages of a rope compared to something that's not flexible? And this is kind of a weird question, but we'll get more at this later in the class. Like, let's say you want to hoist something up off the ground. Okay. If I didn't have something that was flexible, like if I just had a stick with a hinge on it, I'd have to stand above it and pick the thing up, right? What's one huge advantage of a line?
Pulleys.
I could put a pulley up on the roof, right? And then I could redirect the force because the force is going to follow along the flexible line, right? So if I create tension by just using my own body weight to pull down on this thing to create tension in the line, I'm pulling it this way. That force is going to be transmitted through the line, and I'm going to end up lifting up the object. Does that make sense? Right? So there's a big advantage to that. So pulleys, not only will we discover later that you can multiply forces with pulleys, even if we didn't do that, even if we just redirected the force, a flexible line, it makes a lot of sense for us, right? When we're trying to apply physics in a specific way to a situation, right? Okay, so if this thing is from the perspective of the weight here, does it make sense that the only two forces acting on it would be the force of gravity, which is its weight? What is that, by the way? How would we calculate that? If the object has a mass of m, what's its weight? mg, right? Make sense? So weight is always mg. Right? And then upwards, you already told me, would be the tension, right? Because I'm supporting it. From the perspective of my hand, what would the forces be? There's tension down, and then my muscular force up, I guess, right? The applied force is up. Okay. All right, so let's try an example here. You'll see why it's Napoleon Dynamite in a second. This is, I just lifted this out of the book, but out of the online book, but you'll see. So Napoleon Dynamite, not the Napoleon Dynamite, it should just be Napoleon Dynamite. Napoleon Dynamite, who has mass 70 kilograms, walks a massless tightrope made of tensium wire, causing it to sag. Now, the thing about tensium is massless. You also get that at the Acme store. It's very expensive. It's massless.
Who can afford that?
Well,
Bruce Wayne.
yeah, Bruce Wayne can.
How
So
did Napoleon Dynamite get his hand on it?
Oh, I don't know. He's just walking on it. I'm not sure how he got his hands on it. He's just walking on it. But the wire is massless, causes it to sag. When he's at the center of the tightrope, the wire sags by 5 degrees relative to the horizontal. So we want to know what's the tension in the wire. Okay, so what's going on here? So if we were to draw a picture, and I've got a much better one that we'll look at here in a second. So we've got this wire. This wire normally would be, because it's tensium, we can pull it completely taut. It's got no mass. But when he stands on it in the middle, so let's say it's attached right here and right here, when he stands on it, I'm going to exaggerate this a little bit, but when he stands on it, it's just going to do that, isn't it? Right, so he's standing in the middle. There's Napoleon. Right, and so where's the 5-degree angle? Right, that's 5 degrees. That's 5 degrees, right? Okay? So here's a better picture. You see that look like Napoleon Dynamite? Did to me. All right. So here's our picture right here. So if what we want to do then is we want to take this beautiful work of art and we want to make it something a lot simpler, right? We want to just make it into a free body diagram. Well, we can do that, right? Here's the body. And it's right there, isn't it? Yeah, there's the body, it's just a little small. And then we've got the weight vector pushing down. What's weight in this case? mg, so 70 times 9.8, good. And then we've got the tension. Does this make sense that we're going to have where he's standing right there? We're interested in that point on the wire arm, right? That's the point where he makes contact. That's where all the forces are acting. His weight is acting down, and then do you see that the tension has to act in both directions along the wire? What if it didn't? What if it was just like that, for example? He'd fall, yeah, wouldn't he? Because the wire, that would mean it must have snapped or something, right? Then you're going to get this very large net force pointing kind of in that direction. And the wire, that piece of wire is going to accelerate at a high rate. What do you suppose the net force is right there? What's it have to be? It has to be 0. I'll prove it.
Same angle on both sides.
But you could prove it more easily than that. We don't need any fancy
Well,
math.
he's not.
Fancy highfalutin math. Why is the
Well,
acceleration
the line
necessarily?
isn't breaking or nothing.
There's net force. Net force, I mean. Why is it?
It's not moving.
It's not moving. It's not only is it not moving, it's not moving. It's not accelerating, but in this case, it's not even moving, right? Does that make sense? He's just standing there balancing, and it's that point on the wire is not doing anything. It's at rest, so it's got 0 acceleration. If it has 0 acceleration, Newton's second law tells us that there can't be a net force, right? Because net force equals ma. And if A is 0, then the net force has to be 0. Okay, so then it makes sense that this little piece of wire is getting pulled in 2 different directions by the tension, because it's just one piece of all the pieces stuck together in this wire, okay? All right, so now we want to try to determine what this tension is. So how are we going to do this? Let's set up our equations of motion. So what's going to be our coordinate system here? we gotta pick an orthogonal, so a right angle coordinate system. So, what do you think? Let's talk about this. It's not, I mean, this may not seem like an important decision, but it really is. It sets up the rest of the problem.
Wouldn't you want to just pick a normal X, Y, and Z?
Normal, yeah, well, what are the alternatives? I mean, I guess we could pick one where this is one of the directions, but that's kind of goofy. I mean, we'll go vertical. That does take into account one of the forces acts vertically, and so that knocks out one of the three at least. The other two we're going to have to resolve into components. Okay, so then we're going to take this free body diagram and let's just transfer this down to here. So we've got something like, these are both T, right? In this case, I can just call them both T. I mean, I should say T left and T right, but aren't they going to be the same because of the symmetry of the problem here?
Is he in the middle of the wire?
Say it again.
Is he in the middle of the wire exactly?
He's exactly in the middle of the wire. Yeah, exactly in the middle of the wire. So they're both, if he wasn't, and you'll do some problems like this, if he wasn't in the center, do you think the tensions would be the same?
No.
You're right. You're right. They wouldn't be the same. And you'll get a sense of that here soon. So there's the tension vectors, and here's the weight vector pushing down. Right? Those are not necessarily drawn to scale. And we know that this is, I'm just going to call it theta, so we don't have to write 5 degrees every time. The theta is 5 degrees. Okay, 5.0 degrees. Okay. So there's our free body diagram, but we got to go one better than that. We need an orthogonalized free body diagram. Remember what that was? Right? This is, I mean, this represents the forces accurately, but that's not a convenient way to add all those up. The orthogonalized free body diagram is the one that matches the table from previously, right? When we did our vector resolution unit, right? So I've got to break these tension vectors up. I've got to break them up into x components, right? So that's t sub x and y components, both of them, right? Okay, make sense? Okay, so then I have to figure out what those are. So what is, in terms of our triangles here, and those are just right triangles, what is t sub x?
Cosine theta.
Okay.
T cosine.
T cosine theta, everybody agree? Okay, it's going to be the magnitude of the vector times cosine because it's the adjacent leg represents that component, right? So t cosine theta and t sub y then would be
T sine.
t sine theta. Okay, so now let's go down and let's write our equations of motion. Okay, so let's do the horizontal equation of motion. So how do we start that? So that's, what does it represent in this case? The horizontal equation of motion. So, okay, and it's going to be the net horizontal component of the net force, right? So, that. That's what we're representing here. Okay, so we're going to sum all of the horizontal components of any forces up here. Well, let's redraw, you know, I skipped a step. Let's redraw the free body diagram real quick. So now we've got, here's the object. We've got mg pushing down. To the right, we've got t cosine theta. To the left, we've got t cosine theta, right? And then pointing up, we'll make this a different color. We've got t sine theta and t sine theta, right? So how do we do that? All we did, everything was fine up here except all the vectors have to emanate from the body in a free body diagram, right? So these two right here, I've got to slide over so that they're added up tip to tail. And remember, that's a property of vectors. we can arrange them any way we want to. We can translate them around in the plane as long as we don't change their magnitudes or directions for the purposes of adding them. Yes?
Is there a normal force in this?
There is not a normal force in this situation. You explain why. Somebody tell me, why is there no normal force here? What's providing the equivalent of a normal force? Well, normally, like imagine, go ahead.
Is the tension dispersing it between the,
Yeah, right.
the y by k and the x?
Exactly. Well, we're going to see, now imagine he's just standing on the ground in the classroom. Pretty boring. Two forces acting, right? Weight down, normal force up. That's what's supporting him. What's supporting him here?
The wire.
The wire. So it's going to be some component of the tension in the wire, right?
So would that be expressed by the d sine theta?
Well, exactly. That's the sine theta part, because we had to break the tension into components.
And would any of the normal force be in the t cosine theta? No, right?
No, no. And what we're going to see is that, I mean, I guess if you wanted to look at this with a microscope, we have to be careful about picking our system. It's a good question. If we want to, oops, let's go back.
Sit 'em out. See it.
So if we're going to take, let's just take where he's stepping on the cable, like a blown up version of that. So here's a cross section of the cable that he's standing on, right? And here's his foot, right? So from that perspective, it looks an awful lot like the floor, doesn't it? So from the perspective of just this system right here, oh yeah, you could say that there is a normal force. The normal force is the cable pushing upward, right? But from our perspective, we don't really care about that. What we care about is what are the forces that are incumbent on that one spot when we've zoomed out a little bit, right? What's causing that? I mean, sure, the cable has some structural integrity, so the cable, you're not going to fall through it, right? You push down on the cable pushes back up on you. But what's causing the cable to be able to provide that upward force? It's the tension, right? Okay, so we don't really need to think about this one in terms of normal force.
So does that mean that the 2t sine theta would equal the mg?
Right, and that's what the equations of motion will tell us. So if we look at our orthogonalized, that's what we wanted to get right there. Now, once we get that, the equations of motion are simple. We just have to look at the horizontal forces. And if we look horizontally, it's pretty boring. The x component of the net force, we're going to get a positive t cosine theta minus plus a negative t cosine theta because of the directions, and they just add to 0. It doesn't tell us anything, right? So this is pretty much a wasted equation in this case because nothing interesting is going on in that direction, right?
Yeah.
Okay, but the vertical one is the one that's important. So if we look at the vertical equation of motion, the y component of the net force, what are the positive contributors?
2t sine theta.
Okay, yeah, these two, so I've got 2t sine theta, good. So 2t sine theta minus mg equals mass times the vertical component of acceleration, which is what? Is it moving? You already told me.
No.
So it's 0. Incidentally, when we have a dynamics problem like this, where all the forces add to 0, that becomes a statics problem, right? Statics just means no net forces, right? That makes sense. And usually statics problems, not only do they mean no net forces, usually they mean 0 velocity. Doesn't have to, but usually they do. Okay. So what about then this equation? We're trying to solve for t. That's the only unknown because theta is actually 5.0 degrees, right? So we can do that. If this is all equal to 0, this gives us, this equation of motion allows us to do some algebra and solve for t, right? So don't we just get then, if I solve for t, I'm going to add the mg to this side. So T is gonna equal mg divided by 2 sine theta, 2 sine of, well, but I'm trying to isolate the T.
Oh, okay.
So I'm gonna add the mg over here and divide by the rest. And let's go ahead and plug in the value of theta here. So it's sine 5.0 degrees. And now let's pull up our calculator and see, see what this tells us. Because this gives us something pretty profound. So we end up with, if we do that math, so mass was 70, right?
Yep.
So 70 times 9.8 divided by the quantity, 2 sine 5. And wow, that's the tension. Almost, it's almost 4,000 newtons. How much does he weigh? If his mass is 70 kilograms, he weighs a little less than 700 newtons, right? Look at the tension required to hold him up, right? What if we wanted to decrease that angle from 5 degrees to 1 degree? What's that going to do to the tension? Let's just go find out. If we go up and modify this, edit that line so it's sine of 1. I'm in degrees mode, right? Yes, I am. Okay, so if we change that 5 to a 1, look at that. Pushing 20,000 newtons, right? And he only weighs 700. So that's, roughly, not quite 30 times his body weight would be required to, that much tension would be required to hold him up.
Why is it more?
Yeah.
Say it again, why is it more for 1 degree?
Makes sense actually if it's just 1 degree.
Well, that makes sense. Okay, tension's gotta be a lot higher. Let me say when it goes down. Is it because the vectors are, instead of being able to have the advantage of pulling upwards,
Yeah, they pull mostly
they pull
horizontally, don't
sideways,
they?
which means there's more force required.
Right. So I could represent this visually if I did this about. So let's say, let's just look at half of it. I'm not gonna do the whole thing. We'll look at one side of the wire, right? So let's say that we have to, this is the amount of weight that we have to offset. So say that's the amount of vertical force we have to provide to offset the weight, okay? We make that into a vector, so it looks like that. Okay, and so this is gonna be, here's the object, right? So the weight's actually pushing down, but that's what we have to provide to offset it, let's say, with the tension. And look what happens. If that's fixed, right? We have to provide that much vertical force to put this thing in equilibrium, so it's static, right? So what happens if we go at this angle? If we go at an angle of like this, then the vector only has to be that long. See what I'm saying? Okay, but I think this will work. But now if the vector is at a smaller angle, look how much bigger it has to get to have that same vertical component, right? So why is it then that in the winter, your power goes out quite a bit because ice breaks power lines? How come? That happened. This explains it. This explains it. It is. I want to know why is it that a little bit of ice can break a power line?
Because it
Power
only,
goes
it only
out.
adds like that much.
Yeah, it shrinks, causing the tension to go up, making it stop.
Ah, okay, because if as the ice accumulates on the power line, even though the ice itself, the power line could easily support the load of the ice, it was just hanging. But because it's at a pretty small angle, the tension is magnified quite a bit by the weight of the ice magnifies the tension necessary to support the load, right? See what I'm saying?
Crazy.
Yeah, so that's why, it doesn't seem like, you look at a power line, the cable's a thick cable. I mean, it's, it would support lots of weight, except in addition to its own mast, which is heavy, it's got to support that extra ice, and ice is pretty heavy. Doesn't take a huge, I mean, it wouldn't be a big deal. You could easily get several hundred pounds of ice on one of those big, long cables, right? Several hundred pounds, I mean, that gets magnified a lot. You get, I mean, this one got magnified almost 30 times. If it's at a 1 degree angle, that's a pretty small angle. But 30 times several hundred pounds, I mean, that's, you're looking at many, many thousands of pounds then, right? And so you can see why that could happen, okay? Why is it impossible, no matter, I mean, you could take 2 diesel engines on freight trains and you could suspend one little piece of string between them, and assuming the string was strong enough, they could go in opposite directions with full, you know, all the power exerted, and they couldn't pull that string completely taut. How come? Explain that one too.
Is that like an asymptotic sort of?
Okay.
As it gets closer and closer to perfectly level, the force needed to pull it gets greater and greater.
Yeah, exactly. It could never be perfectly level, because even if that yellow vector were really short, if this were truly horizontal, what's the vertical component of the tension? 0, right? So you could never, if the line were truly, you know, and the string has some weight, right? So there's going to be some requirement to be able to, you know, for some vertical forces, because you have to support the weight of the string, right? And so even though, I mean, it's going to get pretty darn close, but even if, I mean, you could have just gargantuan forces. You could have 2 Delta V rockets pushing in opposite directions, and that string would never go taut. It couldn't possibly hit.
So nothing's straight.
No. No, nothing is, I mean, what do you mean by nothing is straight? You mean like,
There's no straight line in the world because nothing is
Wait, what if one?
What about line? Yeah.
well, I mean, you could, okay,
straight edge.
you could engineer something, now we're talking about a line that's flexible. You could engineer a girder so that its weight would, you know, you could put a little bit of an upward bow in it so its weight would draw it down to being straight.
That's why they
Right.
do
And people do that. With civil engineering, that's something you would do. You would account for the weight of the load to make it straight. Yeah, people, that's really what you would do. But no, you could never pull a line totally straight.
Dying right now.
Right? I mean, it could get pretty darn
Are
close.
we gonna have time to finish things at the end of class?
Ever.
Tomorrow you get a full work day.
What if you're
Full
not
on
here
work day.
tomorrow?
Okay, but there's one more really cool thing you gotta see. And this is, so everybody sees how this works, right? So tension is, you know, it's why, okay, it's why, for example, also, well, like if you were to hang, like Grandpa George, my dad was a choker setter for a while, and it was such a dangerous job because think what they would do. You guys don't know about this high-lead logging, but in western Oregon, way out on the west side of the coast, a really hilly country, if they wanted to move a log from the top of that peak over to the top of that peak, you're not going to drag it down and up this rugged country. What are you going to do? Yeah, you're going to run a span across this thing, right? High lead logging, you got these high leads with these big pulleys, and you're going to just, you know, cart this thing across. Well, there's a problem because these logs are heavy, right? Even though they're using just huge braided cable, when it gets to the middle of this thing, of this ravine, the tensions have to be enormous to support this thing, right? And so, even though these cables are just gargantuan, they sometimes would break these cables, and then think about all the force stored in that cable, right? All the tension stored in that cable when it breaks. I mean, that's a tremendous, and we haven't talked about energy yet, but we'll look at this from a different perspective later in the class. There's a lot of elastic energy stored in that cable, and so when it breaks, that energy has to get released. And so what's the cable going to do? It's going to just sweep around, and so those were incredible. Like if you ever, like we're in one of high lead logging, and you heard a cable snap, and you would just, like my dad was in this situation once where he heard you could just hear the thing just whipping through the air. You had no idea where it was going to go. You just got to kind of dive for cover and hope it doesn't get you because it's, you know, you'd be hurt if it ever touched you. But it's.
Is there any way to predict the movement of a?
It'd be pretty hard to do. It's pretty chaotic.
What determines that?
What's that?
What determines the whipping?
Like
Swirly
motions?
Well, it's going to be, there's going to be a lot of, it's going to be the twisting in the cable, so there's going to be some torsional forces, and when it starts to spin, then it's just it'd be so hard. I don't think a supercomputer could model it, because one little fluctuation at the beginning, it's like the butterfly effect, is gonna cause, over time, is gonna cause massive changes in the system, right? And so, I mean, if there was a little gust of wind here, or it hit a twig there, I mean, those little things, when it first snaps, a couple seconds later would completely change the situation, right? So yeah, you can't really predict it. But, so, cables are dangerous, but they can also be really useful. I actually did this once. I want you to see if you can think about how this would work. If you were stuck, and I was stuck in the snow once, and your car is, you want to be able to, you don't have a jack, you don't have, I mean, you want to be able to move your car a little bit, right? Enough to get it onto a place where there's some traction. And let's say you had, hypothetically, you had a tow rope with you. How could, which would be convenient, how could you do this?
Bless you.
You see how this would work? You could put the tow rope, tie it to your car, wrap it around a tree or a boulder, whatever's available, something that's not going to move. And if you apply some perpendicular force at the center of this thing, a person can push with probably a couple 100 pounds of force, right? At least, depending on how much traction you can get. If you can push with a couple 100 pounds here, and it's a long enough cable, it's far enough away so that you get a pretty small angle here, you could generate pretty big forces, right? In what direction is the tension going to be pulling on the car? The direction of the rope, right? See what I'm saying? And so then what you do, and this is what you do, is if there's somebody else with you, which there happen to be, then one person pushes in the middle, and the other person, you just tell her to like what I want you to do is I'm going to stop, and then you're just going to put something under the back wheel so it doesn't roll back, and then you tighten the cable again so the angle's small, and you push again. Take little bites like that. So you push it up, you chock the wheels, then you straighten the cable, push again,
You'd have to move trees,
and
because then you'd get to a point where you couldn't push it because the angle would be too much.
no, but that's why okay, but then it's not effective. It's also not effective, so you can't do that. So if you're ever in this situation, it pays to know how to do this. Like I say, this really did happen. That's why it's such a cool story. So if the cable got too loose, and the angle got too big, like that, see, that doesn't do us any good now, because now I'm not multiplying my force enough, right? See, the tension is more effectively countering the sideways motion. You got to keep the angle really small, so the tension is multiplied a lot, right? Or so your force is multiplies the tension. So you move it a little bit so the angle's small, then whoever's over there, you tell them, okay, put something behind the wheel so it won't roll back. Then you release the cable and you tighten it up again so it's straight, and you push again. And you keep doing that in little pieces, and gradually you move it to a place where you can get it out. Yep.
But going back to our comparison to the 5-degree angle and the 1-degree angle, the difference, would you not want to push as hard as you can on the chain, just the minimal amount, because that'll produce more tension?
Well, you'd want to push, yeah, you want the angle to be as small as possible, right? That's why is that what your question?
Yeah.
So that's what I'm saying. You want to keep readjusting. You want to push it until, and there'll be a point where you can't push anymore, because once the angle increases, then the tension is pushing against you more than the car after, not more than the car, but the balance changes. When the angle is really small, a little bit of tension, a little bit of push buys a lot of tension, right? But as the angle gets bigger, that same amount of push buys much less tension. And so you're going to get to a point where the tension in the rope can cause equilibrium with the point of push, right? The point of exertion of the force. It can stop you then, right? You have to push really hard, but now the tension pulls against you more effectively, and so it stops you. So then you chalk up the wheel so it can't roll back. You pull the line so it's straight again, so it's tight, and you start over again. So you start with a small angle and you push a little, push again, so you can't push anymore. Then chalk the wheels up, tighten the cable, do it again and again and again until you get to a point where the car's out. Yeah.
How long did this take?
It took a while. But fortunately, it was on snow, and so the car moved pretty easily.
Okay, so
Why are you going towards the tree?
Well, because in this case,
the yellow's the mud.
see, that's the mud. You got to get the car out of the mud.
The tree's going in the right spot.
Like
Yeah,
one
but-
person to be in the car, one person.
In what
to be
situation?
driving.
Nobody needs to be in the car.
Drive.
No one's in the car? What?
No, the car's in neutral and you're just trying to roll the car.
Oh. Well, that's what you need to chuck the wheels. That's what I'm saying, like, you need another person back there.
So this really happened?
Yeah.
And it worked?
Yeah, it really happened, coming down from Mount Hood, it really happened. It really, yeah.
Wait, what car?
In my blue Honda.
Why are
You
you
know,
driving?
What's that? No, I was just coming down, it was just really slippery, and we just slipped off the road when we were skiing. So that's what we did, and it worked.
How long did it take?
It took a while, 20 minutes probably, once we got set up.
That's not long at all.
I mean, that's after we got the rope out and put it on there, yeah. You can, and, you know, this is, honestly, I mean, I've done stuff like this a lot. Like, another example is I had to move a dog kennel once, and you can do the same thing. You want to use a chain, because the chain won't flex. If you can, you want to use a chain. You see what I'm saying? The chain won't, that's safe. Chains are safe, because they will never snap back at you. They don't stretch, yeah. Right, cables can be a little dangerous, but if you want to, if you can get two fixed points and you push sideways on some kind of a line, whether it's a chain or a cable, you can provide a ton of force and you can move like a big dog kennel by just pushing sideways on it, right?
Chains can't do break.
Okay, but if a chain broke, it's not gonna hurt you.
It'll whip back.
No, it won't. The chain breaks, the chain just falls if it breaks. Because you can't stretch a chain.
What?
They're rigid links, you can't. If the chain breaks, chains are completely safe. Cables are dangerous, because if you put tension in a cable, it can snap back at you. All kinds of practical stuff you're learning here today.
Chains are safe, that's why they used to make